Okay, so we're up to module 17, the last one for Introduction to Networks. Build a small network. So, we're going to implement a network design for a small network to include router, switch, and end devices. So, we're going to identify the devices in a small network. We're going to look at small network applications and protocols, scaling to larger networks, verifying connectivity, host and iOS commands, troubleshooting methodologies, and troubleshooting scenarios. So, devices in a small network. So, the majority of businesses are small. Most of the businesses' networks are also small. A small network design is usually simple. Small networks typically have a single WAN connection provided by DSL cable or Ethernet. Large networks require an IT department to maintain, secure and troubleshoot devices and to protect organisational data. Small networks are managed by a local IT technician or by a contracted professional. Okay, so device selection for a small network. Like large networks, small networks require planning and design to meet user requirements. Planning ensures that all requirements, cost factors and deployment options are given due consideration. One of the first design considerations is the type of intermediary devices to use to support the network. So factors that must be considered when selecting network devices includes how much they cost, what speed and what types of interfaces they run, how expandable is that, and any operating system features and services that are available. Okay, so addressing for a small network. When implementing a network, creating an IP addressing scheme and using it, of course, is one thing you've got to do. All hosts and devices within a network must have a unique address. Devices that will factor into the IP addressing scheme include the following. So all of your end user devices, and they could be wired, wireless or remote. Servers and peripherals, and so of course they may well have static IP addresses. And of course the intermediary devices being switches, access points and probably a router or two. It is recommended that you plan, document and maintain an IP addressing scheme based on the device types. The use of a planned IP addressing scheme makes it easier to identify a type of device and to troubleshoot problems. Okay, redundancy in a small network. Now this is less common, but should be. You should try and get redundancy if you can. In order to maintain a high degree of reliability, redundancy is required in network design. Redundancy helps to eliminate single points of failure. Redundancy can be accomplished by installing duplicate network equipment, and it can be accomplished by supplying duplicate network links for critical areas. And so you can see here that we've got more than one router, more than one switch, and more than one link to each server. And of course, there's more than one server, so you've got redundant servers as well. So if one of these devices fails, the network will continue to work. Of course, this is not going to be a mum and dad business with about 5 people in it. This is probably going to be a bit bigger than that, but yeah. So traffic management. The goal for a good network design is to enhance the productivity of the employees and minimize network downtime. The routers and switches in a small network should be configured to support real-time traffic such as voice and video in an appropriate manner relative to other data traffic. A good design will implement some quality of service, certainly. Priority queuing has 4 queues. The high priority queue is always emptied first. And so, as you can see here, basically with the queuing, your high priority queue, that will always be emptied first. When that's empty, that's when it will actually go to the medium priority queue. Both of those queues need to be empty before you actually use the normal priority, do the normal priority queue. And so carrying on, the top 3 queues must be empty before you use the low priority queue. Okay, so small network applications and protocols. So after you have set up your network, your network still needs certain types of applications and protocols in order to work. The network is only as useful as the applications that are on it. So there are 2 forms of software programs or processes. You've got network applications, which of course are implemented with the network in mind. And so they actually have an implementation application layer protocols and are able to communicate directly with lower layers in the protocol stack. So, you know, web server and whatever it might be. Application layer services for applications that are not network aware, but programs that interface with a network and prepare the data for transfer. And so basically, a bit like we were talking about SMB in the previous chapter for the application layer, you know, Microsoft Word is not really a network aware application, but you can save to a network drive because there is that application layer protocol SMB, server message blocks, that sort of pretends you've got a local drive when it's actually a remote drive and things like that. So that's an example of that. Okay, so some common protocols. So network protocols support the applications and services used by employees in a small network. Network administrators commonly require access to network devices and servers. The two most common solutions are Telnet and Secure Shell. Secure Shell, of course, is the preferred. When it comes to web servers, HTTP is used. And then there's HTTPS, which needs to be... there's no S in that second bracket there, but anyway. Simple mail transfer protocol is used to send email. Post office protocol or IMAP are used to receive emails. File transfer or secure file transfer protocol are used to download and upload files between a client and an FTP server. DHCP is used by clients to acquire an IP address from a DHCP server. Of course, DNS is used to resolve domain names to IP addresses. So certainly you're going to need these two bottom layers in most of the time. The upper layers, well, you know, most of us will use a web browser. Most of us will use email. A file transfer protocol, you know, you may or may not use. But of course, files will be involved, and so if it's not FTP or SFTP, it might be SMB or something like that as well. Now, a server could provide multiple network services. For instance, a server could be email, FTP, and SSH server all at the same time. All right, so these network protocols comprise the fundamental tool set of a network professional, defining processes on either end of communication session, types of messages, syntax of the messages, meaning of the informational fields, how messages are sent and expected responses, and interactions with the next lower layer. Many companies have established a policy of using secure versions of those protocols, so SSH instead of Telnet, SFTP instead of FTP, and HTTPS instead of HTTP, wherever possible. And actually, you know, especially when you talk about the browsers these days, they actually try to use HTTPS every time, and they only go back to HTTP if the server doesn't support HTTPS. So voice and video applications. Businesses today are increasingly using IP telephony and streaming media to communicate with customers and business partners, as well as enabling employees to work remotely. This last year, it's been a very, very busy thing. The network administrator must ensure the proper equipment is installed in the network and that the network devices are configured to ensure priority delivery. The factors that a small network administrator must consider when supporting real-time applications are the infrastructure. Does it have that capacity and capability to support those applications? VoIP is typically less expensive than IP telephony, but at the cost of quality and features. IP telephony, this employs dedicated servers from a call control and signaling, and then real-time applications as well. So the network must support a quality of service for mechanisms to minimize latency issues. Real-time transport protocol and real-time transport control protocol are two protocols that support real-time applications. So scaling to a larger network. Growth is the natural process for many small businesses, and their networks must grow accordingly. Ideally, the network administrator has enough lead time to make intelligent decisions about growing the network in alignment with the growth of the company. So to scale a network, several elements are required. So network documentation, so both physical and logical topology diagrams are certainly useful. A device inventory, so you know what devices are on the network already. A budget, of course, you need to know how much you can spend on maintaining the network. And traffic analysis, protocols, applications and services and their respective traffic requirements should be documented. These elements are used to inform decision making that accompanies the scaling of a small network. Okay, so protocol analysis. It is important to understand the type of traffic that is crossing the network as well as the current traffic flow. There are several network management tools that can be used for this. So to determine the traffic flow patterns, it's important to do the following. Capture traffic during peak utilisation times to get a good representation of different traffic types. Perform the capture on different network segments and devices, as some traffic will be local to a particular segment. Information gathered by a protocol analyzer is evaluated based on the source and destination of the traffic as well as the type of traffic being sent. This analysis is used to make decisions on how to make the traffic manage the traffic more efficiently. All right, so employee network utilisation. Many operating systems have built-in tools to display such network utilisation information. These tools can be used to capture a snapshot of information such as the following: the operating system and its version, CPU utilisation, RAM utilisation, drive utilisation, non-network applications, network applications. Documenting snapshots for employees in a small network over a period of time is very useful to identify evolving protocol requirements and associated traffic flows. So verifying connectivity. So whether your network is small and new or you're scaling an existing network, you will always want to be able to verify that your components are properly connected to each other and to the internet. The ping command available on most operating systems is the most effective way to quickly test layer 3 connectivity between a source and destination IP address. The ping command uses ICMP, echo request, and echo reply messages. And so the echo request is type 8 and the echo reply is type 0. I think we actually looked at that on Wireshark, didn't we? And so, of course, that's a very quick way of verifying connectivity. Now, on a Windows 10 host, the ping command sends 4 consecutive ICMP echo messages and expects 4 consecutive ICMP echo replies. The iOS ping sends 5 ICMP echo messages and displays an indicator for each ICMP echo reply received. Now, of course, you get a full line from Windows. With iOS, you just get a character for each one. And so if you get an exclamation mark, that's good news. The echo reply has returned. It validates the layer 3 connection between source and destination. A dot means that the time expired, and so that echo reply didn't come back in a timely fashion. Now, it might just be a temporary situation that dot didn't happen. That dot happened, and of course, if it's your first connection, there might be the odd ARP request that it had to wait for, and that can maybe get you have a fail for the first packet. And then a U indicates a router along the associated path, means send a message saying destination unreachable. Possible reasons include the router does not know the direction to the destination network, or it could not find the host. So the last router on the link could not find that host, so it's not up. Other possible ping replies are Q, M, question mark, and ampersand. However, the meaning of them are not spoken about today. All right, now on Cisco iOS, you can actually do an extended ping. Now, you need to be in privilege exec mode, and instead of typing ping in the target, you just type in ping, and basically you go through a dialogue asking you a whole pile of questions. And so then, of course, if there's something in brackets, that is the default setting, and so you can just hit enter and it'll take that. And so here, of course, there's no default setting for the target, so of course you need to supply an IP address or host name. 5 packets is the default. Of course, you could say 10 or 100 as well. Datagram size, so if you remember Windows, it's normally 32. iOS, it's 100 bytes. And then you can set the timeout time. Now, extended commands, basically you can set a few different things that are non-standard. And so because we're sitting on a router, there's actually going to be more than one IP address that you can send it from. Now, by default, the router will use the outgoing interface that will get to that destination as the source address. Now, that might be a little bit trivial for a reply. And so if you want to test that your routing protocol is working properly, you might actually use a different interface address as the source. And so instead of your WAN link to the rest of the world, you might actually want to use your internal Ethernet address as the source address. And so you can actually do that, and you can change a few other things as well. Not that you'll do that very often. So once it's gone through all the options, it'll send out the pings. In this case, we had a 100% success rate, so all very happy. Now, ping is, as I've probably said before, a very binary kind of thing. It either worked or it didn't. You've got two options. So trace route will actually tell you the path that the traffic is taking, and that's nice. Not always useful, but nice. But if it's not, if you're not able to connect to that destination, it might actually tell you roughly where your problem is, and so it helps with troubleshooting. And so, as I said, however, it does not identify where the problem is located along the path. That's ping. Trace route can help locate layer 3 problem areas on a network. A trace returns a list of hops as the packet is routed through a network. The syntax of the trace command varies between different operating systems. On Windows, it's trace RT. On Cisco, it's trace route. But if you just type in trace, that's enough for it to be unique. And so I've rarely typed the entire command in. And so again, you can do a destination. And so on Windows, this is what it looks like. And so in this case, we've only had successful connection, well, with one device along the way. And that's, I'm assuming that's your own router, because 10.1.1.10, oh no, that's the destination, sorry. We actually don't know this device's IP address. And so to me, it looks like we got a response from our own router because it's hop 1 and we got nothing else. Now you might get some stars along the way if that particular router has been set not to respond to echo requests, because in that previous chapter we were talking about reconnaissance. Well, ping is used for reconnaissance, so some people don't reply to it. But if you seem to get a string of one after the other of just these stars, Control-C will get you out. And so basically, the next hop after your nearest router, there's a problem. Now, these are trace routes from a Cisco router. And so on the left, the trace validated that it could successfully reach PCB. On the right, the host was unavailable, or not. It could not be connected to. So the output shows asterisks where replies timed out, and so of course they indicate a potential problem. So of course Control-C is on Windows, Control-Shift-6 is what you use on iOS to cancel that. Now, Windows implementation of traceroute sends an ICMP echo request. Cisco iOS and Linux use UDP with an invalid port number. And so the final destination will actually send an ICMP unreachable message saying ICMP port number is unreachable if it gets all the way. Now, you can actually do extended traceroute. So much the same as you could do extended ping. You can just type in traceroute and go through the options. Now, with Windows, the traceroute command allows the input of several parameters through options in the command line. However, it's not guided like the extended traceroute iOS command. So basically on Windows, you've got to do your help command and see what options are available. And so you can force using IPv4 and IPv6, and there's a few other. You can modify the source address used. You can set your timeout. You can set a maximum hops, and -D is don't do DNS for all your host names. Okay, so the extended trace route, the interface is very much like the extended ping. It enables the user to create a special type of trace by adjusting parameters related to the command operation. Extended trace route is entered using in privilege exec again and typing trace route. And if you don't supply that destination, it will ask you those questions again. And so again, you'll be prompted for options, and of course you can specify. different options. Of course, that's the point of doing it. Okay, so a baseline. So basically, once you've built a network, you should actually test how it's working. And that's basically creating a baseline. And so this is how the network performed when it was new. And so later on, if you've got some kind of problems or maybe heavy traffic that's slowing it down, you can actually compare the readings from that to something else, which of course means that makes those readings a lot more meaningful. And so one of the most effective tools for monitoring troubleshooting network performance is to establish a network baseline. One method for starting a baseline is to copy and paste the results from an extended ping, trace, or other relevant commands into a text file. These text files can be time-stamped with the date and saved into an archive for later retrieval and comparison. Among items to consider are error messages and response times from host to host. Corporate networks should have extensive baselines, more extensive than what we'll talk about today. So there are professional grade software tools available for storing and maintaining baseline information. So of course Windows Server comes with a lot as well. So host and iOS commands. So IP configuration on a Windows host, of course, is ipconfig. We've pretty much already spoken about that. We're all doing Windows as well at the same time, are we? Okay. So of course ipconfig is the command line version. You can go to the Network and Sharing Center and have a look at the details as well. But ipconfig is normally my go-to because you've got to go through about 3 or 4 different windows in the GUI to get to it. Command line, open that, type ipconfig, done. And so ipconfig by itself is very basic information, but you get your address, you get your subnet mask and gateway. If you want more information, you can actually do ipconfig/all, and that will actually give you a lot more information. And so it'll give you your own MAC address as well, and you know who your DHCP server is and all kinds of things like that. Now ipconfig, you can also basically do your DHCP requests with it as well. So if you do ipconfig release, we'll actually close your lease on any address you might have from your DHCP server, and ipconfig/renew will actually get you a new lease. The DNS client service on Windows PC also optimizes the performance of DNS name resolution. By storing previously resolved names in memory, the ipconfig/display DNS command displays all of the cached DNS entries on your system. So you can actually have a look at your DNS cache by doing ipconfig/display DNS, and it actually shows you the DNS cache, which can be handy at times. Now on Linux, it's not ipconfig, it's ifconfig. And no, Linux was first. So now ifconfig is a little different to ipconfig. It shows you a whole pile of information, but some of it's a bit different to the way Windows does it. But it does give you your internet address, gives you your mask. It also tells you things like broadcast addresses and all kinds of stuff like that as well. It also gives you some statistics on the interface, what's been going on. Now, on the Linux, IP address command is used to display addresses and their properties. It can also be used to add or delete IP addresses. ifconfig can actually be used to configure things as well. Now, it may look a little bit differently on different iOSs. Now, on Mac, on a Mac OS host, you can go to Network Preferences Advanced to get the IP addressing, or it's based on Unix. And so ifconfig will also work. And so other useful Mac OS commands, you can do network setup, list all network services, or network setup, get info, and that'll tell you. ARP, pretty much spoken about ARP a few chapters ago. So ARP command is executed from Windows, Linux, or Mac. The command lists all devices currently in the ARP cache of the host. So ARP-A command lists all known IP address and MAC address bindings. To ensure that the ARP cache is populated, ping a device so that you can have an entry in the ARP table. The cache can be cleared by using net shell interface IP delete ARP cache. Now, you need to have administrative rights to be able to do that command. Also, you can do the ARP command ARP-D*, and that will actually clear your ARP cache as well. But you still need to have an administrative version of the command line open to be able to do it. Okay, so iOS commands. So of course, show running config shows you the current running config that's in RAM. Show interfaces gives you pretty much a page full of information per interface, lots of information. Show IP interface is more about the layer 3 information as opposed to generic information. Show ARP gives you the ARP cache. Show IP route gives you the routing table. Show protocols tells you what layer 3 protocols are running. Normally it's just going to be IPv4 and maybe IPv6. And then show version actually tells you what version of the operating system is running. It also tells you about the hardware on the device as well, so how much RAM, how much, what interfaces are included and things like that. Now, show CDP neighbors. CDP provides the following information about each CDP neighbor: device identifiers, address list, port identifier, capabilities list, and platform. So basically, it will tell you about your neighbor, and so the device ID. So a neighbor of R3 is the device called S3. And here the capability is S and I, which means it's a switch, and it's a smarter switch that actually looks at IGMP messages. And so platform, of course, is what model of switch it is. And so here it tells you it's gigabit 001 on R3 that connects to fast Ethernet 05 on switch 3. And basically, this time will be valid for another 122 seconds. Basically. Now, so show CDP. We will go into more depth than that if you do 5CRS. I'm assuming you'll do it more then. So basically, CDP is Cisco Discovery Protocol, and so it's a Cisco proprietary protocol, and so only Cisco devices understand it. And so basically they can communicate with one another and share information. Now it can be very handy if you're dealing with a network that has no diagrams or documentation for you to find out things. You can actually figure out, well, on gig 001 on R3, we have a link to fast Ethernet 05 and S3. So you can actually start drawing a diagram about how they're connected. And so that's very useful. The downside is there's no security included with CDP, and so if someone can intercept those packets, well, and they're a hacker, they'll get that information too. And so a lot of people actually turn CDP off. Anyway, so the show IP interface brief command, I think I might have demoed this for you more than once. So on a router, of course, you get all the layer 3 interfaces and their IP addresses and their status as well. On a switch, yes, you'll get all the layer 2 interfaces, but of course they don't have IP addresses, and so you'll normally only get it on a VLAN interface on a switch. Finally, we're done. So, no, we're not done, sorry, it's troubleshooting. So best troubleshooting approaches. And so basically, there's a process, and there is often some iteration in this process. So basically, the first step you need to do when someone's reporting a problem is you try to identify what the problem is. And so although tools can be used in this step, a conversation with the user is often very helpful. So you ask them what happened, when it happened, a few other pertinent questions. Did you install some new software on your computer recently? And all kinds of things like that. And so once you've gathered information from the user, as well as maybe from the network and other places. You then need to establish a theory of probable causes. And so there may be several possible causes, of course. And so from there you would probably try and choose the most probable cause and try and see whether that's the problem. So then you test your theory on your most probable cause. And so from there, how you test it, of course, depends on what the cause might be. And so you test your theory, you try and fix that problem. If it does fix, great. And so you need to establish a plan of action and implement the solution. You need to verify that you've fixed it. If you have fixed it, great. You might want to make sure that you can prevent that from happening again. If you haven't fixed it, back to step 2. What's another probable cause? And so basically you may well have to go through these steps a few times before you actually get the problem solved. Because your first guess may not be the right guess. So if you've made any changes and it hasn't fixed it, you should probably undo those changes and look for another cause. So once you've actually found the correct cause and you've fixed the problem, maybe you've implemented some preventative measures if that's possible, you then of course document your findings, actions and outcomes. And so the beauty of that is, if this problem happens again, you should hopefully have some kind of database management system where people can look up those symptoms and then it will actually list, well, last time this happened, this solution fixed it. And so hopefully that will get them to the correct solution quicker. All right, so resolve or escalate. So basically, in some situations, it may not be possible to resolve the problem immediately. A problem should be escalated when it requires a manager's decision, some specific expertise, or network access level unavailable to the troubleshooting technician. The company policy should clearly state when or how a technician should escalate a problem. So basically, when you're talking about help desks, there's normally 3 levels of staff. Level 1 staff are the ones who normally take the initial phone calls. Of course, it does depend on the size of the help desk. And so those level 1 staff, so let's just say you're working at an ISP, they're going to be your level 1 staff. They will normally have a script to follow to ask questions about what's going on and what the problem is and so on. Now, some common problems that happen all the time, they may well have a solution that that level 1 technician can implement. Away you go, great, done, fixed, happy customer. Other times it's a little more in-depth, a little more unusual. That's when you might need to escalate it to a level 2 or level 3 person, depending on the problem. And so that is when you have someone with more specialist knowledge in that particular area. And that's basically what they're talking about here. All right, so when it comes to Cisco devices, there is a command called debug. Now, we've done a lot of show messages, show commands before. Show interface. Now, that gives you a summary of stuff that's happened since that device booted up. And so if that device has been on for 6 weeks, the statistics it shows you is going to be 6 weeks worth of statistics. That might be helpful, it might not be. All of the problems might have happened in the last 10 minutes. So you can clear the counters and watch again, and that might help you a bit. But debug basically shows you things as they happen. It's not a summary, it tells you things as they happen. And so the command allows the administrator to display OS process, protocol, and mechanism and event messages in real time for analysis. So as something happens, if you've got that feature debugging, it will send a message to the console as it happens. All debug commands are entered in privileged exec mode. You can't do it through user exec. Cisco OS allows for narrowing the output of debug to include only the relevant feature or sub-feature. You should only use debug for troubleshooting specific problems because it actually uses resources on the device And if it's using the resources for that, it's not using it for forwarding people's data. So to list a brief description of all of the debugging options, you can do debug question mark. It's going to be a lot of options. Now on Packet Tracer, there's only so many debugging ones implemented, but on a real device, there's going to be a lot of debug options. To turn off a specific debugging feature, you can do the no debug command. There is also the undebug command as well, and that will turn it off as well. Now what I often do, because sometimes with debug there can be tons of information coming out of that, and it's very hard to type into the command if it's just data buzzing past. What I'll often do is I'll do undebug all first, and then I'll do the specific debug command that I want to do, and then to get rid of it, all I have to do is up arrow twice, hit enter, and it'll recall that undebug all. And so that is my easy way of getting out of it. Be cautious using some debug commands, as they may generate a substantial amount of input and use a large portion of system resources. The router could get so busy displaying debug messages that it would not have enough processing to power to perform its network functions, or even listen to commands to turn off debugging. So you can see that there's undebug all. You can actually type in debug all, but that's going to be a very, very busy display. And it's often going to be faster than what can actually come out of the display as well. So, now debugging goes to the console, and by default that's the only place it goes. But of course, if you're telnetted in, you're not actually on the console. You're on the VTY, and so you can turn on debugging from Telnet or SSH, but you won't actually see it unless you turn on the terminal monitor option here. Now, debug and certain other iOS messages output is not automatically displayed on remote connections. This is because log messages are prevented from being displayed on VTY lines. To display those messages, use the terminal monitor privilege exec command to stop logging messages on a terminal, using the terminal no monitor command to turn it off. Now what I'll often do, and if I'm doing debugging on a remote machine, I'll actually open up two Telnet sessions. One of them I'll use to interact with, and the other one I'll do that terminal monitor and just let any of those debug messages go to that. So that's the way that I separate the interface from the output. And so that's my process for doing it, and it hasn't failed me yet. And so I can still do undebug all on the one I'm using as an interface, and it'll actually turn off the debugging messages to the other VTY. Okay, scenarios. So interconnecting network interfaces must operate in the same duplex mode for best communication performance and to avoid inefficiency and latency on the link. And so duplex mismatches can certainly cause a problem. The Ethernet auto negotiation feature facilitates configuration, minimises problems and maximises link performance between two interconnecting Ethernet links. The connected devices first announce their supported capabilities and then choose the best performance option of those. If one of the two connected devices is operating in full duplex and the other is in half duplex, that mismatch occurs. While data communication will occur through the link with a duplex mismatch, it will be poor performance. And so duplex mismatches are typically caused by a misconfigured interface or in rare instances a failed auto negotiation. Duplex mismatches can be difficult to troubleshoot as the communication between devices still occurs. But you'll normally get a whole pile of console messages telling us that it's happening. 2 common causes of incorrect IPv4 assignment are manual assignment mistakes or DHCP related issues. Network administrators often have to manually assign IP addresses to devices such as servers and routers. If a mistake is made during that assignment, then communications issues with the devices is likely to occur. So an iOS device use the show IP interface or show IP interface brief commands to verify the IPv4 addresses that are assigned. And so, of course, shown is an example here. And so just check that those addresses are the right addresses. Now, for end devices on Windows, when a device cannot connect a DHCP server, it actually gets an address that starts with 169.254. So we have mentioned a PIPA in types of addresses, and that's what it's used for. A computer with a PIPA addresses will not be able to communicate with other devices in the network because those devices will most likely not belong to that range, unless they all can't talk to the DHCP server, and then they might be able to communicate, but they won't be able to talk any further than their own network. Other operating systems don't use a PIPA, so those Windows devices are never going to talk to them. If the device is unable to communicate with the DHCP server, then the server cannot assign an IPv4 address to the specific network in the device and will not be able to communicate. To verify the IP addresses on Windows, of course, you use ipconfig command. So 169.254, that is a big red flag saying, oops, something went wrong. Now, default gateway issues are another problem. So if an end device needs its gateway to be able to talk to remote hosts. If the device has an incorrect or non-existent default gateway address, it will not be able to communicate with devices on remote networks. So it's similar to an IPv4 addressing problem, but yeah, it will normally be either manual or DHCP problems, so someone got it wrong somewhere. And so again, you can use ipconfig to verify that the gateway information is correct. On a router, use the show IP route command to list the routing table and verify that the default gateway is known as a default route has been set. Okay, DNS issues. It's common for users to mistakenly relate the operation of an internet link to the availability of DNS. If you're using names and it doesn't work, it doesn't mean your link's down. It could mean that DNS is down. So again, the host is told its DNS server, often either manually or via DHCP. Although it is common for companies and organisations to manage their own DNS servers, a reachable DNS server can be used to resolve names. Cisco offers OpenDNS, which provides secure DNS service by filtering phishing and some malware sites. OpenDNS addresses are X and Y. Advanced features such as web content filtering and security are available to families and businesses. Use ipconfig/all as shown to verify which DNS server is in use by the Windows computer. The NSLookup command is another useful DNS troubleshooting tool for PCs. And so DNS, so you can NSLookup cisco.com or google.com and see how that works. Now we've finished the topic. So when it comes to choosing devices, of course, you need to look at cost, speed, what types of ports and interfaces, how expandable the device is, and what features and services are available from the operating system. When implementing a network, you need to create an addressing scheme and use it on the end devices, servers, peripherals, and intermediary devices. Redundancy can be accomplished by installing duplicate equipment, but it also can be accomplished by supplying duplicate network links for critical areas. The routers and switches in a small network should be configured to support real-time traffic, such as voice and video, in an appropriate manner relative to other data traffic. There are two forms of software, programs or processes that provide access to the network. So network applications or ones that use application layer services. To scale a network, several elements are required. So network documentation, a device inventory, budgeting, a budget and traffic analysis, so to grow networks sensibly. A ping command is the most effective way to test layer 3 connectivity. Cisco OS offers an extended mode of ping where you can actually add extra parameters. A trace returns a list of hops as a packet is routed through a network. iOS also has an extended trace, much the same as the extended ping. Network administrators view the IP addressing information on a Windows host by using the ipconfig command. You can use /all, /release, /renew, and /display DNS to do some other things as well. Verifying IP addresses on a GUI and Linux machine will differ depending on the Linux distribution and desktop interface, but on the command line, ifconfig or IP address are the commands you can use. The GUI on the Mac, there's Open Network Preferences Advanced, or again, you can use ifconfig or network setup on the command line. ARP command is used from Windows, Linux, and Mac, and so you can get a listing of IP to MAC address relationships. Alt-A, of course, is what gets you that list. Common show commands are show running config, show interfaces, show IP address, show ARP, show IP route, show protocols, and show version. There's also show CDP neighbor, which is useful as well. You can do show CDP neighbors detail, and that will actually give you a lot more information per device instead of just one line. Show IP interface brief command outputs all interfaces on the router and their IP addressing information. So the six basic troubleshooting steps are: 1, identify the problem; 2, establish a theory of probable causes; test the theory to determine the cause; and then 4, establish a plan to action and implement the solution. Then you verify the solution, and then you document your findings and outcomes. Problem should be escalated when it requires a decision of a manager, some specific expertise or network access level unavailable to the current troubleshooting technician. OS processes, protocols, mechanisms, and events generate messages to communicate their status. The iOS debug command allows the administrator to display these messages in real time for analysis. To display logged messages on a terminal, use the terminal monitor command. There is the logo, finally. All right, so that is chapter 17, the last in the introduction to networks. And so from here on in, we will actually start using switching, routing, and wiring essentials. Wireless essentials. And so we'll go on with chapters from that.